Yeah, thanks a lot. So, yeah, I would, as the title says, I would like to say something about some kind of a Monge-Ampere equation which emerged some years ago, and it arguably plays the same role in the geometry of certain quaternionic spaces as the complex Monge-Ampere equation plays in the case of the complex spaces. So, the rough plan is that I would like to outline you firstly the things which can be Calabi-Yau type theorems. As a motivation for our study. Then I would like to say what's actually the quaternionic Calabi conjecture. And finally, how it reduces to, and some basic stuff about the quaternionic Monge-Ampere equation. Okay. So this is the outline. Okay, so let's do first things first. So let me very briefly remind you. So suppose we have a complex manifold. And we are considering a Hermitian metric on it. So a Hermitian means that G is an inner product on our real manifold, and in addition, it satisfies the property that it's I invariant. Right? So let me just make a brief remark, a very silly one. So why, when you are dealing with complex manifolds, only a Hermitian metric actually makes it makes sense only to consider Hermitian metrics? Well, it's because if not, then by taking into account the complex structure, you would like to impose the condition that the inner product is actually C-linear in both entries, but it's impossible, as easy exercise shows you that such an inner product has to be degenerate then. So it's natural to consider on complex spaces the so-called Hermitian sesquilinear form. So let's call it H. So this is a guy which, in a standard form, takes such an expression. So now it's C-linear in the first entry and C-antilinear in the second entry. It's non-degenerate in a sense, or positive in a sense that if you plug twice the same, you get something positive. And if you swap the entries, you obtain the bar of the result. Okay? But this corresponds, as an easy linear algebra exercise tells you, to actually looking at c to the power n as r to the power 2n, and now inducing the inner product, which you can take to be the real part of this form. Well, you have to keep the data what was actually the complex structure. So in this picture, I is just the standard complex structure. And now to those two guys, you can naturally associate what we call a Hermitian form. So now the real part of this guy, this G, will satisfy the property of being Hermitian. That's why we are playing only with such inner products on a complex space. Because if you take the real thing of this one, which is naturally considered in Cn, then this will be Hermitian. And now the omega, this Hermitian form which I mentioned, is actually obtained by twisting J on the first entry. So this is a real positive 1-1 form, as a complex geometers say. And now from those two data, you can actually unwind everything and reclaim capital H by saying that capital H is actually G minus I omega. Actually, it's twice. It's 1/2 of that, but we don't bother about the constant. Okay, so let's keep this in mind actually, because it will be beneficial in this second part. Okay, but now let me recall you what's a Calabi conjecture actually. So now we are not playing with any complex manifold endowed with some Hermitian metric, but only with spatial Hermitian metrics. So if you have a Hermitian manifold, then let me just recall you that we say that G is scalar provided that the associated Hermitian form is closed. Okay, There are many equivalent ways of saying what's a Kähler manifold. You can, for example, say that it's the same as requiring that the Levi-Civita connection actually preserves not only J, but also I. And this actually tells you that Kähler manifolds are nothing but a Riemannian spaces with spatial holonomy, because this condition together with information that Levi-Civita preserves G tells you that the holonomy of that is contained in UN. Okay, and now when you have a complex space, naturally you can associate to this the first Chern class. So this is a certain class which can be defined in, let me write it that way. So this is a little strange thing in here. If you are not a complex geometer, these are just those, you just take those representant in the second theorem class, which are of type 1, and are real. Okay, so it turns out that on a Kähler space, if you take the Ricci tensor of G and you twist it by I on the first entry, and by the way, for the rest of the talk, I will still denote this by Ricci, even though not mentioning that I'm twisting on the first entry. This is only in order to make this a differential form. And now on a Kähler manifold, actually this represents the first Chern class. Okay, and the question of Calabi was whether actually this is all you can obtain in C1. So if for every rho which is in C1, there exists G which is scalar, such that rho is equal, let's say, the G tilde, Ricci of G tilde. Okay, so this, as most of you know, was solved by Yau in 78. And this is done by solving the so-called complex Monge-Ampere equation. Let me just briefly tell you why this is solved by solving the complex Monge-Ampere equation. This is because for a Kähler metric, the expression for this twisted Ricci curvature is very, very simple. So suppose that your metric G is written as Gij bar dzi J. Okay. Then it turns out that Ricci G is precisely minus I dt bar of log. So these are the so-called Dolbeault operators. So these are certain operators. This one differentiate in the holomorphic direction. This one differentiate in the anti-holomorphic direction. So I imagine if you already knew what that is, it tells you nothing. If you didn't, it still tells you nothing. So either way, it's logarithm of the determinant of this matrix. So here are the indices for the entries of this matrix. Okay, and now, so now let's put tilde here, because we would like this one to be equal to rho, right? But now rho is the representant of the first Chern class, and I told you that whenever we will start with some Kähler metric, Ricci will always represent the first Chern class. So rho, since it's also in this class, has to differ from that guy by d of something, right? So this is precisely equal minus I dd bar log Gij bar, where now this is a fixed reference metric. So we start with some fixed metric and we are looking for this one, okay? Plus some d of alpha, let's say. But actually, on a Kähler manifold, there is so-called dd bar lemma, which tells you that if you only differ by d of alpha and you are of right by degree, then actually you have to differ by dd bar of something. Okay, so I can write here actually, let me check the sign. Okay. So now we see that we obtained an equation. This has to be equal to this. So now this, if you plug everything under IDD bar, you will get that this plus F equals 0. And now this is certain second order PDE. So the maximum principle tells you that actually this guy inside has to be constant if you are on a compact manifold. So this gives you the equation that log Gij bar tilde, determinant, let's say plus some C, because I told you that this function has to be constant. So let's suppose that this C is 0. And now if you take e to those powers, you will obtain the expression determinant of the metric you are looking for is equal determinant. Let's say e to the power f. Okay. And now another easy linear algebra exercise actually tells you that suppose you are now, you will multiply both sides by the volume element of the metric. So you multiply by dz1 wedge, dz1 bar wedge, the rest. Okay, then the expression of the left-hand side actually will be omega tilde to the power n, where omega tilde is the Hermitian form associated to this metric, to the Hermitian metric you are looking for. And this is precisely what we call the complex Monge-Ampere equation. Now, in such a form, it's still not a concrete PDE because we did not specify what kind of omega tilde we are looking for, and I never remember whether it was already in this Calabi paper or not. But actually, it turned out that it's extremely fruitful to assume that omega tilde is actually in the class of omega. Because again, the DD bar lemma then tells you that this has to be omega plus I DD bar phi, or for some function phi. And now you plug it in, and you will obtain such an equation. So here, omega is known, it's a fixed form, and you are looking for a function phi. So this depends somehow on second derivatives of phi. So this is certainly a second order PDE. This is nonlinear because you are taking the nth wedge power of those forms. So it's probably not that easy to solve, and it's really not that easy, but it can be solved. Okay, and this is like the story of the Calabi conjecture. Let me now make a small remark towards those Calabi-Yau type theorems. So now in this picture, you can actually forget the scalar assumption. So suppose I was not assuming that omega was scalar. Surely you will have to make some adjustment. I don't want to speak about all of them because, well, first of all, these will fail if you put it word by word. But still, this equality is true provided you are not putting here the Ricci curvature of the Levi-Civita connection, which is no longer like allowed even to take in the Chern-Weil isomorphism, but you can take the so-called Chern connection here and put here actually the Ricci, one of the Ricci curvatures, the one which is obtained by tracing the endomorphism part of the curvature of the Chern connection, and plug it here and ask now whether every representative of the first Chern class is now the Chern-Ricci curvature of Hermitian metric of certain type, where type is now what you would like to place in the place of a scalar assumption. Okay, so let me write it in a way of a question. So question is as follows: fix Mi, this is the complex space, and C a subspace of all the Hermitian metrics of Mi. And now you are asking if for every row in C1, let's write it both churn. It's not that important. We would like to ensure that now the question will be only about the guys which differ by IDD bar of something again. Whether for every such a guy, there exists an omega tilde in C now, such that the Ricci of the churn connection for this Hermitian structure is equal rho. Okay, so this is a little maybe messy, but once you put C, the scalar cone, and you assume that it's not empty, then you precisely get the Calabi conjecture. So now if you assume that C is the cone of so-called Godeschon metrics, you will obtain the Godeschon conjecture, and this was solved recently by Székely-Hidi, Tossati, and Wainwright. I think it was 15. Okay. Now, also a very interesting question is when you put C to be the cone of balanced metrics. So Godeschon means that the Godeschon metric is also determined by some differential condition, namely that DD bar of omega to the power n minus 1 vanishes. So now, if you take balanced metrics, so well, first of all, it's still not solved. But yeah, I heard like many people talking about this problem. Tossati was interested in this problem. I also heard Yau himself talking about this problem. So this is slightly related to finding this, let's say, canonical metric on threefold, for example. So we have a threefold, and you know somehow that either C1 is 0 or even that the canonical bundle is trivial holomorphically. Can you find a balanced metric with the Chern-Ricci curvature equals 0? Okay. Yeah, so this is not known, and I will relate to this question actually in the second part of the talk, which now starts. So now we would like to speak about the quaternionic version of this Calabi conjecture, which I described. Okay, so in order to that, we have to remind what's actually a hypercomplex manifold. So a hypercomplex manifold is the one which is endowed with the 3 complex structures, such that they satisfy the relation that if you multiply them, you obtain minus identity. So actually, once you have the 3 of them, you have the whole sphere of them. So you take all the complex structures which can be written in that way. For the vector A, B, C of norm 1. And actually having such a sphere of complex structure is the same as reducing the structure of the tangent bundle of this manifold to the general linear quaternionic group. Like the complex structure is nothing but reducing the structure to the general linear complex group. But now we have to be a little touchy about the integrability condition. So I don't want to go into like too many details, but let me just tell you that it's not true that locally the hypercomplex manifold looks like the quaternionic space to the power n. It's actually a very rare situation. So having M endowed with 3 integrable anti-commuting complex structure is the same as having this associated quaternionic structure weakly integrable, in the sense that you have a torsion-free connection which preserves it. But by no means the structure is constant in some local frame. Okay, so this is the remark. And yeah, so now once we have a hypercomplex manifold, it's actually again natural only to consider those Riemannian metrics, which we will call now hyperhermitian, of course. And they are defined by the property that they are L invariant for every L in this Quistor sphere. Okay. So again, a very quick reminder from linear algebra, and this will be the last one, so please do not go to sleep. So now the same story on Hn. So this is the, let's say, quaternionic vector space. It's only natural to consider such a forms capital H, which are now, let's say, H anti-linear in the first entry, H linear in the second entry. They are positive in a sense. If you plug twice the same, you obtain something positive, and if you swap, you obtain the bar of the result. So you can like formally write that the standard one is dqi, hence bar dqi. Okay. But these are quaternion valued forms, so you have to be very, very cautious. This expression doesn't make any sense. But you can play the same story which I showed you in the beginning, and you can now look at h to the power n as c to the power 2n actually. And this is done in the following way. So if you have a quaternion Q, then you can always decompose. Let's say we have the tuple pattern, so let's introduce the index. So you can always decompose it in the following way. And this allows you to look at quaternionic vector space as a complex vector space. Okay. And now we would like to, so having this, we have to remember what was the action of J. And now we would like to find the lacking metric data, which will encode the capital H. So from the real angle, of course, you can take just the real part of this form, but we would like to look from the complex angle. So let me, just without going to the details, because we don't have time for that, so let me just write you that. If you take the standard inner product in Hn, so the Euclidean one, when you look at that as r to the power 4n, then H can be actually written in terms of this inner product in that way. But now, since we are going towards the complex picture, you can group those terms in these two groups and write it as H bar plus J omega. Because if you write in a local coordinate, so suppose that you are evaluating capital H on two tuples of quaternions, and so suppose that you have H of Q, where you decomposed P into Pi into Z I plus J Z to I plus 1, and you decomposed Qi into V to I plus J I plus 1. Then this form will be equal precisely to ZK bar WK, where K now runs over all indices from 1 to 2n plus, and this will be this part, plus Z to I W to I plus 1 minus Z to I plus 1 W to I. And you recognize in here that it's nothing else but the standard holomorphic symplectic form dz to I wedge dz to I plus 1. Here is, of course, summation over I. And it's also not very hard to see that this is actually obtained by twisting this Hermitian sesquilinear form by J on the first entry. Okay, so now closing this picture, because I can imagine you can be tired by this linear algebra exercise. Having this is precisely as having c to the power 2n with some j, Hermitian inner product or Hermitian squilinear form, and capital omega, which from now on we will call the hyperhermitian form, with certain properties, namely that this Hermitian guy is J invariant up to the bar, so this has to be satisfied. So now we are lacking the bar, and capital omega is obtained now by twisting this Hermitian form by J on the first entry. And the whole point is that omega still controls the whole picture. So from omega, you can cook up again the small h, and from those two, you can cook up the capital H by this formula. Okay, so yeah, this was the last linear algebra exercise. And now, just the last thing before stating this analog of the Calabi conjecture in this hypercomplex setting. So we would like to speak a little bit about the analog of Calabi-Metrics. So, well, arguably, of course, from the point of holonomy, you would say that the analog of the Calabi-Metric is the hypercalametric. Okay, so let me just briefly recall you. So, G, let's say M, I, let's say S2. We'll only keep the sphere to the right less. So this is hypercala. For example, if the associated hyperhermitian form is closed, it's more common to know this condition as d omega I equal d omega j equal d omega k equals 0. And this is equivalent to having this this metric having a holonomy in SPN. Okay, but this is in case of a compact world, a very restrictive condition, because we know a handful of examples. So let me introduce an intermediate class in between the hyperhermitian ones and the hypercala ones. So we would like to have something in between. And those are the so-called hypercala with torsion metrics. Okay? So how can you spell out the hypercala condition in one more way? Well, you can say that actually all of this is equivalent to the fact that the Levi-Civita connection of the associated metric is equal to the bismuth connections with respect to 3 induced Hermitian structures. So the bismuth connection, when you have a Hermitian manifold, a bismuth connection is just a connection, a complex connection or Hermitian connection. So it preserves metric, complex structure, and its torsion is a skew form. It's a differential form. In general, torsion is just 2-1 tensor, so you can of course lower the upper index, you will obtain some 3 tensor, but by no means you will always get a 3 form. Actually, it's pretty rare. Okay, so now you will say that you are hypercala with torsion, provided you lose this last, arguably the strongest condition, because it forces this common condition to have a vanishing torsion. Okay. And it turns out that if you forgot about this equality, again, this hypercala with torsion condition has a very nice differential, just equivalent condition, because instead of requiring that the associated hyperhermitian form is closed, you assume it only to be declosed. Okay, where this is the 1-0 part with respect to I. Okay, so we have the analog of the, arguably we have the analog of the Cala metrics, and let me now spell out the quaternionic Calabi conjecture.
Sorry, so
yeah.
Hypercala with torsion, the Levi-Civita connection is equal or not equal?
No, not equal. It's equal in case of hypercala, because then this, of course, this common connection then preserves everything. It preserves I, J, and K, and G. So it shows you that it's without torsion, and it has holonomy, of course, contained in SPN, because it preserves the quaternionic structure and the metric. Here we still have a common connection which has holonomy SPN, but this connection has a torsion. That's why the name Hyperkala with torsion, because it has the same holonomy as in the Hyperkala case, but the connection is far worse because it has a torsion. Okay. So now there was a conjecture some years ago. It was of Alesker and Verbisty. I think it was 2008 or something, around 10. Okay, and it's of course motivated by the original Calabi conjecture, but formulated in terms of this associated complex Monge-Ampere equation. So let me just, yeah, I actually didn't tell that. So from obtaining this complex Monge-Ampere equation here, you actually see that solving the Calabi conjecture is the same as being able to prescribe any volume form to your Kala metric, right? Because this is the volume form associated to the metric you are looking for. So solving the original Calabi conjecture is being able to prescribe any volume form you like. So now, let me firstly make a side remark that if you have this hypercomplex, then the canonical bundle with respect to any complex structure, but let's just fix I for a moment. I will explain in a minute that it does not depend on any choices, actually, what we are doing, but let's focus on I for a moment. Then this is always trivial, topologically, because remember that we are no longer in a Kala case. So this is trivial because you can, for example, take the capital omega to the power n, and this will give you the non-vanishing section. But by no means it has to be holomorphic. Okay. And now, since we can naturally associate to any hyperhermitian metric this omega, the quite natural question arises whether every section of that guy arises that way. So the conjecture is for every, let's say, theta, which is the section of that guy, is there, let's say, G tilde, and suppose your original wasn't only hyperhermitian, but it was HKT. Is there an HKT metric such that the associated complex volume form equals to that guy you have chosen? Okay, so first of all, let me tell you that, well, you can of course argue how natural this translation of the language between the complex and quaternionic case is, but for sure this question is not trivial, because like in the Kala case, the hyperkala condition is not preserved under conformal perturbations. So it's not that you can say, okay, let's start with the HKT metric we have, so this one associated to omega, and let's just rescale that. You cannot do that because only the constant conformal changes, which is trivial from this condition. So if you have e to the power f here, then if you do the wedge, you will actually obtain that d of that guy has to be constant. Okay, so yeah. So let's try now to reformulate this in terms of some second order PDE, which would be nice. And this will be the PDE, which we call the quaternionic Monge-Ampere equation. Okay. So yeah, the question is, okay, of course you can say that the section has to be of that form, because this is the fixed one. Okay. So the right-hand side looks nice. Now the question is how, because for sure somehow you would like to perturb the original one, right? So what to put here? And in order to answer that question, let me tell you that Verbisty, around 2000, introduced the following operator, dj, let's just call it that way. So now we are defining it. You don't have to know what that is. And it's just defined by twisting the Dolbeault operator by the J complex structure. So if you do the exercise, you will see that this operator actually increases the holomorphic index. So it goes from PQ forms to P+1Q forms. That's because the J operator swaps the indices. So it changes PQ form to QP forms. And now, why am I saying about that? Well, because suppose that we will play an idiot approach and we would like to guess that this perturbed omega tilde is still in the class of omega, let's say in the rank homology, but you assume that it's of proper by degree. Then, not always, but under certain additional assumptions on your HKT manifold, there is the DDJ lemma. So if you assume that omega tilde is omega plus D of something, it's actually DDJ of something. So, okay, so we have a candidate then, because since we have started with translating complex case, let's translate it till the end. So you'll guess that you should perturb by this second order expression. And this guy, that form, by the way, this is an 2n0 form. So this is the section of your canonical bundle is equal to that guy. Okay. Let me now tell you, so this is called the quaternionic Monge-Ampere equation. And let me just briefly justify why this is called I thought that there is third one, okay.
Oh, yeah, it's the third one.
It's underneath.
Underneath.
Underneath this one? Or?
Yeah.
It's
No, no.
fixed on the wall.
But there's one which is not moving, right?
Yeah. Ah, okay. Ah, okay. Ah, so it's great. Okay. Either way, so we have this equation. So let me just write it here because we will keep it until the end. So just why it's called the quaternionic Monge-Ampere equation now? Well, the complex Monge-Ampere equation is called the complex Monge-Ampere equation because it's the determinant of the complex Hessian. The real Monge-Ampere equation, if you know what's a real Monge-Ampere equation, it's not hard to say what's a real Monge-Ampere equation. It's just you try to prescribe the determinant of the Hessian of your real function of your Hessian. So you take the matrix of second derivatives and you want that of that to be right. So now, why this is the determinant of some quaternionic Hessian is the question, if you would like to call this the quaternionic Monge-Ampere equation. And this is the case because if you do the calculations in the flat space, so in Hn. So now the ideology is weaker because remember that this is not the local picture always, it's only sometimes the local picture. But either way, let's play that. And let's take phi in here. Then you have the so-called Fouetter operators, which apparently were considered already by Fouetter in the 30s. So you have the operators which are as follows. You take df over, let's say, dqi bar, and you declare that this is equal d phi over dx, if these are the real parts of this quaternion. And you define this guy just in order to have the following property. Then you can cook up a matrix of the second order derivatives with respect to those operators, right? And arguably, you can call it the quaternionic Hessian. So the Hessian of phi is just the matrix of d square phi dqi bar dqj. Okay. So now let's call this guy capital H phi. In a sense that we look now on this matrix in h to the power n as some as the induced hyperhermitian sesquilinear form. So you put one vector in front of the matrix, one after, and you have a form. Now, if you recall this linear algebra exercise, this produces us certain guys, small h and omega, right? So let's just look at the associated omega phi. It turns out that if you compute omega phi to the power n, if you compute omega phi to the power n, you will precisely obtain ddj phi to the power n. And this, of course, can be called the quaternionic Hessian, because, well, you still have to write something, but yeah, this is defined through the quaternionic Hessian, so we can argue that somehow it is the determinant of this matrix. Okay? Great. So this tells you why the name. And the equation can be interesting because it encodes some, let's say, naively defined but not trivial question. Of course, this HKT condition here is not crucial in any way for writing the equation, because even if you have just a hyperhermitian metric, you can still write the equation. You, of course, lose the fact that now the DDJ perturbation maybe is not the natural one, but still, the complex Monge-Ampere equation is interesting even on any complex manifold, not necessarily the Calabi one, even though perturbing by the complex Hessian is not natural anymore in that situation. So you are actually interested in solving this equation under as general assumptions as possible. Okay, so let me now give you some information on what is known. So I have the 10 past or
10 more minutes, 15 more minutes.
okay. So what is known? Well, the first general type result is by Alesker himself. It's around 12, I would say. So it tells you that provided M is a flat torus, you can solve the PDE, which is pretty heavy restriction on the manifold, but remember that it is highly nonlinear PDE, so actually solving in any case is hard. And this is one of the two only installations where actually the problem is solved. There are other results under additional assumptions. So, for example, some Italian people, for example, Gentili and Vezzoni, they are able to solve the equation, but provided they assume some invariance of the data. So, for example, that they are on so-called nil manifolds, and they assume some invariance of the right-hand side, and they can find an invariant solution. Well, this still gives you a hope, because it tells you that in some cases actually the conjecture is true, so you can solve the equation. But nevertheless, the problems which you are dealing then are quite different, right? Because if the equation becomes invariant, then actually it reduces to some other PDE. And here actually the problem is that we cannot handle this PDE, right? So, but even that, those are pretty interesting results. So they are from like 2020 and 2021, I think. And the only other known case when you can solve the equation for any data is if you start with omega being hypercala, actually. So this is a result of Dinev and myself from 21. So we are able to solve it always, but we have to assume that the starting omega is hypercala. Actually, we can solve it. This is not written explicitly in the paper, but it's only important that we can take a hypercala metric. So we can actually solve the equation on a hypercala manifold, but it's not much more because there are a handful of examples. So this is very rigid assumption, and it's not natural from the point of the original Alesker and Verbisty conjecture, because then you assume that the starting metric is better, but of course this perturbation by no means will give you another hyperkähler metric. So you started with hyperkähler, then any non-trivial perturbation will not be a hyperkähler. It's quite easy to see. Okay, so what are actually the problems? Let me say a little bit about the problems. So the problems are, of course, the a priori estimates, because if you have such a PDE or any PDE, one thing you can try is to try the continuity method. So the continuity method is that you try to deform your equation. So parameterize the right-hand side, make it dependent on t in such a way that for t equals 0, you have some kind of a trivial equation, or at least the equation which you can say is solvable. While at the end of the parameterization time or space, you obtain the original equation. Now your goal is to show that the space of times for which you can solve the equation is open and closed. Openness is usually the easier one, but by no way always easy. Nevertheless, it's easy in that case. So you just have to show that this operator, let's say if you divide both sides by omega to the power n, that this operator, which goes from certain Banach spaces, like smooth functions to smooth functions, is invertible. And this can be shown. So now the problem is the closedness of this set of times where you can solve. And in order to show that it's closed, well, you have to show that if you have a sequence converging to some T0 on the borderline, then the T0 is still in the set. And for that, you need the so-called a priori estimate. So you need to know that the solutions will be bounded whenever the right-hand sides are bounded, because then for this sequence of converging times, you will have bounds on the right-hand side. And if you have the a priori estimates, you will have the bounds on the solutions. And then you can take the convergent subsequence because they will be bounded in some Sobolev space. Okay. So the problem are the a priori estimates. And let me just, in the remaining 10 minutes, let me just tell you what are the known a priori estimates and what are the problems. So surprisingly, the C0 estimate is known always. So let me write it in a way of theorem. So MSG is hyperhermitian only, then the C0 norm of F is bounded in terms of a constant which depends only on M and right-hand side, of course. And let me give you the account, because it was actually proven over a quite big span of the time. So the first version of that was by Alesker and Verbisty. Alesker and Verbisty. And it was already in this paper from 2008. So they showed the estimate under the assumption that this guy is actually holomorphically trivial. That looks a little suspicious, but roughly what's the reason? The reason is they tried to use the Moser iteration like the original Yau's paper. In order for this Moser iteration in case of complex Monge-Ampere on Kähler manifolds actually works mainly because omega is closed. So for the Moser iteration, you need to have the L2 norm bound on the gradient. For that, you do certain integration by parts. And now in this integration by parts, if omega in complex case is closed, you don't get the crash terms. So in here, we do have some integrability of the capital omega in the HKT case, because we know that it's declosed. But the associated volume form can only be written as, let's say, omega wedge, omega bar to the power n. So now if you do the integration by parts, then well, by hitting this with omega, you will not get the trash terms, but with omega bar, you will get the trash terms. So repeating the Monge-Ampere iteration is not that trivial, actually. And it was done much later by me. I think it was like 19, where you need some technical refinement of the Monge-Ampere iteration, like in Tosati and Weinkoff for the complex Monge-Ampere. Okay, so they were able to show this C0 bound for the complex Monge-Ampere, also bound by Monge-Ampere iteration, but there you have many trash terms and you have to somehow deal with them. So it turns out it's possible also in case of the quaternionic Monge-Ampere equation, but still under the hypercala with torsion assumption, because this tells you that there are some trash terms, but less than in general hyperhermitian case where you have even more trash terms. Okay, so another result was by Alesker and Verbisty. So this was under the assumption that M is locally flat, in a sense that hypercomplex structure is flat, which is pretty rigid assumption because it tells you that the manifold is affine actually. Okay, and in order not to skip anyone, I think these are all the known results before the last one. This was also by myself, and it was only recently. And this result is without any assumption on the hyperhermitian metric. So we have generic hyperhermitian metric, and moreover, which can be actually interesting, the bound is as sharp as possible. So in complex Monge-Ampere equation business, for example, it's pretty popular subject to discuss how sharp the bound can be. Nowadays, it's for the Calabi conjecture itself, it's not important because we know the smooth solutions always exist. But in this problem, we still do not know actually whether it's always solvable. So having a sharp bound can actually be useful because maybe it will be the case that in some cases you will only have a weak solutions, and then you can discuss the regularity of that. So this sharp result tells you that this depends only on LP norm of the right hand side for any p bigger than 2, and this is as sharp as you can go, contrary to the complex case when you can put any p bigger than 1 in here. Okay, so this is about the C0 estimate, and let me just very briefly, because probably I'm okay, I still have 5 minutes. So now the higher order bounds. So so a priori, of course, you need any order a priori estimate, but if you are already like in a PD business, then you know that you need much more actually. So in case of this quaternionic Monge-Ampere equation, since the operator, if you write it in this way that you divide this by that form, this operator is also convex in certain sense. And it tells you that all you need is the C2 estimate, a priori estimate on your solution. So in this result, which I mentioned you with DNet, we're able to show, so let me just write it as one of the results. So with DNet, we have the gradient estimate, which is interesting in its own right, because it's not always the case that for the Hessian type equations, you can obtain the gradient bound. So we have the bound on the gradient of phi, explicit one, and we have the bound on, so yeah, the whole strategy is that we obtain that one, then we obtain the bound on the Laplacian, and from that one, we can obtain the bound on the full real Hessian. But here are slight differences with even with the Taylor situation in the original Calabi conjecture. So in the original paper of Yau, you do not need a gradient bound. Here we do use actually a gradient bound at this moment to obtain this bound. Okay, so it's a little different. And despite that, we also use the Hyperkähler assumption. So I haven't written. So we also use the Hyperkähler assumption heavily. And these are the only known results in general, let's say. So under some assumptions on the metric or manifold, but no all the other higher order estimates are known for these equations. And in the last, let's say, 2 minutes, if it's fine, let me just tell you what are the problems actually, why it's apparently so hard to get the higher order bounds. So in order to that, I would like to now write in local coordinates the equation. So it can be painful, but it will be painful only like for a second. So suppose we work in a holomorphic coordinates for the complex structure I. So we have the holomorphic coordinates for I. Okay, and then of course you can write omega phi, which is omega plus dj phi. This can be written as, well, this guy depends purely on the initial data. So let me just write it that it has some components. It's omega ij of the, let's say, if we write in holomorphic coordinates, then it depends only on the metric and the second complex structure, in the sense that on its components. Plus, now this guy, well, a priori you have here dj to the power minus y d bar of that. This is equal to that. So in theory, you are differentiating even j, but this weak integrability of the hypercomplex structure tells you that this actually depends only linearly on the j complex structure. And it can be written explicitly, actually. Let me not try to do the exercise. Yes, so this can be written as minus phi ik bar, jk bar I, where those are, of course, the coefficients of j in the frame associated to these holomorphic coordinates, and these are the usual complex derivatives of phi. Okay. Okay, so this is the expression for omega, and now, well, what? Times, let's say, dzi wedge dzj, and of course we make the coefficients to be anti-symmetric. Okay, so we then because we can always swap, right? So now,
sorry, but are those two different phi's, or you just written it in a different way?
Yeah, sorry, this is the same phi. Yeah. Thanks.
Okay, so okay, great, thank you.
This is just you compute this form in local coordinates. And now the equation, well, the equation is you take the n power of this form, right? And we have the coefficients. So what's that? This is precisely the Pfaffian of this skew-symmetric matrix, right? So the equation in those coordinates takes the form Pfaffian of this matrix. Thus, okay, let me write it quickly. Okay, so now, how usually the higher order bounds are derived? Well, suppose to fix the attention, you would like to derive the gradient bound. So you take some quantity, let's say capital eta, which is somehow dependent of the gradient. It's some expression of the gradient. So now we would like to take some differential operator of that, usually the linearization of this equation. So you are doing all those computations, you obtain some terms in here, right? And of course you will the goal is, of course, to show that, let's say, this Laplacian, you know that it satisfies this at the maximum point, and you would like to derive the estimate on that guy from this information. But now, in order to exploit this, so in order to leave only the required quantity and bound all the other quantities, you have to somehow use the information from the equation. So you have to differentiate the equation to plug in into those expressions which you have here. And now the problem is that when you differentiate this equation, unlike in the real or complex case, you first of all have not only the terms which depend on the derivatives of the original metric, which are here, but also the terms which depend on the derivatives of the fixed background second complex structure. So now you have two types of problems instead of just one type of problem. So you have two types of bad terms. What is even worse is that there are also, those guys pop out also in front of phi. So when you differentiate, you also have the terms depending on the curvature in terms of the derivatives of phi, which makes it hard to exploit from this differentiated differential equation the expression which you like. So this is one. This is like problems from one side. So you have the curvature of G, but also of hypercomplex structure. And this is usually not flat. But even if it's flat, then there is a second type of problems. So, and in order to really anticipate that, I would have to write much more, but let me just tell you that. This is the quaternionic Monge-Ampere equation. So let's put it in a framework of real complex and quaternionic equations, okay? When you are doing estimates for the real equations, the situation is actually the best possible because there is no splitting of types of terms which you are obtaining when differentiating the equation, but by which I mean, for example, in a real case, you can write that the gradient is actually phi I squared, let's say, phi j g I j, right? Now, if you take, for example, Laplacian, differentiate it twice, in the result, you will actually obtain twice phi I j bar squared, right? Now, in the complex case, you will already have a bar in one place. And if you do the compute the Laplacian of that guy in complex coordinates, you will obtain not twice something, but two types of terms. Phi ij, where here you have the holomorphic differentials, here phi ij bar. So we have different terms, and actually you can use only one of them usually in the computations because second one is unknown because it depends on the original guy, and this can be like not controlled in any way because it depends on the guy you are actually looking for, more or less. And so this the only one which you are usually using, and this is just enough. So in case when you are doing the real estimates, you use only half of that and you obtain the estimates you want. You just can throw away the second half. In the complex case, you have to use that one. You are left with that one, but that one is not useful anyway. In the quaternionic case, you also have some kind of splitting into the quaternionic, let's say, ideologically, holomorphic and anti-holomorphic derivatives. So we also have splitting into two types. But now this one type which you can a priori use is half too small to what you would like to have to bound in a visible way, the bad terms. So unless one cannot figure out a new way how to exploit these terms which usually were just leftovers, then it seems rather unlikely to solve the problem by the known approaches. Okay, so yeah, I imagine I'm already like a little after a scheduled time. So yeah, let me stop here.
Other questions or remarks?
So for your result, when you assume that the metric is a hypercalar, so it helps deal with the.
No, this still is there, but it helps not to deal with the curvature terms. And once you don't have them, you can trivially say that those guys are positive. You don't have to use them to bound anything coming from the curvature. So you don't have to use them in any way besides telling that they are just positive. So the hypercalar assumptions allows not to deal with this problem. And once you are not dealing with this problem, you do not have to use actually this one in clever way. But once you have this, then it's like no middle ground. Once you have those, all the problems are there.
So to derive the first C0 estimate, you are using Cologny's approach, or
Well, yeah, actually in those methods, so
instead of using the Moser iteration and so on?
yes, so no, in this last paper, actually I used something quite new. So there is recently a series of research on obtaining Cologny's estimates by PDE methods. So mostly Fong and his collaborators at Columbia and also Rutgers have a series of papers of that. So I coupled that with some old trick. So this is purely PDE. There is no pluripotential in that. And the idea is to compare your equation with some fixed equation. Compare the solution with that guy to the solution of some fixed equation. So this idea is pretty old. So it's also like Xu Wang, I think, had an ideas like that.
It doesn't use capacities and stuff like this.
Not explicitly. No, capacity not in any way. It uses these sublevel sets, but the method does not depend on capacity in any way. So yeah, it actually gets rid of this only point in Cologny's proof, which was truly the pluripotential one. So the one when you well, there are two, but one is you can trivially show that the capacity of the set where the solution is very small is small, and then you have to show that it actually controls the Lebesgue measure, and this is the problematic term. So they are in these recent approaches, they are able to get rid of this completely. So this is purely PDE, but maybe the surprising actually in this result is that you take as the equation for comparison with that one, the complex Monge-Ampere equation. So you also have to couple it with some version of trick of Cheng and Yau. They had this idea to compare actually the real equation with the complex one. And by that method, you can cheaply obtain the L2, the C0 bound for the complex Monge-Ampere, which depends on L2 norm of the right-hand side, but not the sharp one. But now it turns out that by coupling this recent method of Fong and Guo, actually, with this version of that trick, so you are not comparing the real and complex operators, but quaternionic and complex, then coupling those two things, you can actually cook up the sharp estimate, despite you are still relying on the idea, which in complex case was not giving you the sharp bound. But of course, in a complex case, you were not using this techniques of Fong and Guo because they were not there at the time.
And you didn't discuss about uniqueness?
Uniqueness is trivial.
Uniqueness is trivial.
Because you can, that's because it's written in terms of products. So you can subtract the both sides. Suppose you have phi and phi primes. Suppose so you subtract both sides. So you have 0 on the right hand side, and here you can use here. Okay, let me just write. So you can write that it's equal. Okay. So yeah, if you write omega phi minus omega psi to the power n, let's say, so suppose these are two solutions. So actually the difference will be omega phi minus omega psi, because these are wedges of forms. That's why what I'm writing makes sense. And this is now only the product of those guys, right? So this guy is positive in certain sense. It actually makes sense to say that it's positive. And this guy is precisely the, let me do the, it's dj of phi minus psi, right? I am not that mistaken probably. And now you can bound this by something fixed from below and say that it's Laplacian or whatever.
And you didn't discuss about the stability. So if I change exponential f by exponential of f plus epsilon. How does phi change?
Well, this is precisely the estimates actually, right?
You get something like this I'm saying if we change f by f plus another function, right?
Yeah,
Which is more in a certain sense.
yeah.
Then you
Are asking how far
is the solution?
well, but because I'm just not sure if I'm following, isn't the C0 estimate telling you that?
Okay,
Yeah, in the sense, yeah. But what would you like to know then?
we like to have. Ecology has a similar result.
You mean
So we have
stability?
two right-hand side which are, and he has a way to compare the solutions.
Yeah, that's formal. That's formally something different. Yeah, I don't have like exactly something like that, but I think this could have been achieved cheaply, I would say,
Okay.
in a crude way, because again, in those stability estimates, it's also like very curious and important how good is the dependence of the right hand side of this change of f, right? So, but
I'm sure it's going to be a consequence of.
yeah.
I was wondering if you already did.
No, because yeah, so far I still like hope for getting the.
So you're completely convinced of the
I would
future.
Yeah, I would be really surprised if it's not the case, because you cannot solve the real equations, but in their case you have all the higher order bounds. You just don't have the C0 bound for the real Hermitian type equations, or the by the real equation I mean, for example, you have a Riemannian manifold and you take the equation determinant G plus the second covariant derivative of phi, and you would like to describe that. So, but here the problem is the C0 estimate. For the complex Monge-Ampere, you have all the bounds, and since here you have the C0 bounds, yeah, I would be really surprised, because it would mean actually, since you have the C0 bound, that probably you are able to solve it, but in some very weak sense. Which would be very surprising to me. And from the PDE point of view, it's, there is this recent series of works of Harvey and Lawson. So apparently, in local cases, because they treat only the local case. So either you have the Dirichlet problem in a domain, or you have a domain on a manifold which supports certain geometric structure, and then you consider all the equations I was discussing today in a unified framework. So the real complex and quaternionic equations, and even much more general equations. And it turns out that, of course, the results for all those equations are not that as sharp as for those standard equations, real, complex, or quaternionic, but they do hold more or less with weaker estimates or less regularity, but they do hold. So yeah, I'm convinced that it has to be true. Even in hyperhermitian setting, yeah. It's like, since you are able to solve the complex Monge-Ampere equation on any complex manifold, you have to be able to solve this equation on any hypercomplex.
In the assumption,
yeah,
sectional curvature or something like this could help, or
arguably the hyperkähler assumption is actually a weaker assumption, right? Because hyperkähler assumption does not give you any bound like that. The curvature is positive or no negative, though it's Ricci flat, so it's like you can look from different angles. But yeah, like the holomorphic bisectional curvature probably won't help you, because it's like, again, in real equations, you have to have that the sectional curvature is positive. In complex case, you have to have that holomorphic bisectional curvature is positive. So here is just different types of curvature terms which appear. So of course, we do have like some notes in our computations with Sławek that if some of those terms which are cooked up from this omega are positive, then you are able to solve the equation. Because we
Geometric interpretation.
yeah, they don't have, they are just zero when omega is hypercala, and hypercala is pretty natural assumption. So we put the paper in that way because it's the only like something which won't scare the reader from the spot. But there are of course some like 3 lines or maybe 2 lines assumptions that if this is positive, this is positive, this is positive, then you have the solution. But it's I didn't even try to find an example which is not hypercala and satisfies that because it's one, probably not doable, and second, not that interesting, I think. It just tells you again that if you don't have a problems, then you don't have a problems, then you can and you can solve the equation. I mean, these assumptions that those terms are positive, actually.
Okay, I think we should stop there.
Yeah, I was there.
Thank you. Other question in the audience online? We are sorry we started late due to a technical.
Everyone is already out.
They are all gone, I think. Thank you.
Julia, how
Peut-être quelqu'un voulait intervenir, non?